All right, get ready, because today we are exploring one of the absolute most fascinating engineering challenges of our modern infrastructure.
Welcome to my new video on integrated safety and security in railway systems. Today, we're diving into a massive digital puzzle that is happening right under our feet and on train tracks all across the globe.
So here's the game plan for today's explainer. We'll cover safety versus security, the digital railway vulnerability, the certification catch-22, the black channel approach, built-in defense mechanisms, and finally, future-proofing our railways. Let's get right into it.
Part 1, Safety versus Security. Okay, let's set the stage here with some foundational definitions.
You know, people throw around the words safety and security like they're the exact same thing, right? But in engineering, they are totally different beasts. Safety is all about protecting us, the humans, from the machine. It's preventing accidental harm. Think of those automatic train doors. If you're walking a bit too slow, sensors catch that and stop the door from crushing you. That's failing safely. Now, security? That's about protecting the machine from humans. It's preventing malicious harm. Things like passwords and firewalls specifically designed to keep unauthorized people out of the system.
Moving on to Part 2, the digital railway vulnerability. Let's look at how this actually plays out in the real world.
Because the reality is the landscape of our railways is changing at lightning speed. For decades, trains relied on these heavy, closed-off mechanical systems. But today, we've shifted to open digital protocols to really boost efficiency. Take the ETCS, the European Train Control System. It's great because it creates a common platform that lets trains travel seamlessly across different countries. But, and this is a massive catch, by moving to these highly distributed, wireless computer networks, our trains are suddenly incredibly exposed to external cyber attacks. It's a huge trade-off.
So to make absolutely sure these massive moving machines fail safely, the rail industry doesn't mess around. They rely on this incredibly strict family of standards called the EN 5126. The big one, EN 5126, dictates RAMs. That stands for reliability, availability, maintainability, and safety. Literally, every single component has to be rigorously tested and certified to prove that a random hardware failure won't cause a disaster.
But here's where it gets tricky. Contrast those hyper-specific safety rules with our current security standards. If an engineer wants to secure a train network against a hacker, they're stuck relying on generic ISO or ISA frameworks. These are just broad standards meant for everyday IT or general industrial systems. There just hasn't been a universally mandated hyper-specific security standard built exclusively for the railway sector the way there is for safety.
Which brings us to Part 3, the certification catch-22. This mismatch creates a literal nightmare for engineers. It's a three-part catch-22. First, if you just mix a security module in with a safety-certified module, boom, it fails safety certification because the security part wasn't built to those strict railway standards. Second, cyber threats evolve every single day. Security needs constant updates. But in the rail world, if you change even one line of code in a safety system, you have to completely recertify the whole thing, which is unbelievably expensive and slow. And third, why not just encrypt the data? Well, encryption takes processing time. In a system where a train needs to hit the brakes immediately, a millisecond of latency from decryption is an absolute deal breaker.
So that leaves us staring at the ultimate engineering puzzle of this explainer. How on earth do we secure a critical system from modern hackers without completely breaking its rigorous safety certification?
Well, let's look at the solution in Part 4, the black channel approach. Engineers came up with a genuinely brilliant workaround here. It's called the black channel. Think of it like this. Imagine sending a locked, heavy-duty safe through a totally sketchy, untrusted mail carrier. You don't actually need to trust the mail carrier, or in this case, the communication network, if the package itself has built-in ways to detect if it's been tampered with. The network is essentially treated as a black box that we just assume is completely unsafe.
In practice, this means safety standards actually allow certified and non-certified systems to share the exact same physical network. No way, right? But the trick is placing a thick layer of built-in defensive mechanisms right on top of the standard communication protocol. Because those mechanisms guarantee the data hasn't been messed with, the underlying network itself doesn't need to pass those impossibly strict safety certifications.
Part 5. Built-in defense mechanisms. So how does this actually work? What exactly is keeping our data safe? Well, we use some surprisingly simple but incredibly effective logic tools. Take a sequence number, for example. Every message gets one. If a hacker intercepts a message and tries to replay it later to cause a crash, the sequence number will be out of order, and the system just throws it in the trash. Or think about timestamps and timeouts. If an attacker delays a message while trying to manipulate it, the system sees it arrived too late and just ignores it completely. These were originally designed to catch random electrical glitches, but guess what? They do double duty and catch malicious cyber attacks too.
And finally, Part 6, Future-Proofing Our Railways. Let's see this in action.
The absolute key to making this whole thing work in the real world is physical separation. We use an intrusion detection system, or IDS, but it is completely isolated from the safety-certified module. They share the same network, sure, but they operate totally independently through that black channel. The IDS is like a digital guard dog, just constantly sniffing the network for intruders or anomalies, but it has zero direct physical links that could ever interrupt the train's actual safety tasks.
The pure genius of this physical separation is that it completely obliterates that catch-22 we talked about earlier. We can push security updates to the IDS every single day to fight new malware, and we never have to touch or recertify the critical safety modules. We can even bring in third-party security vendors to diversify our defenses. And best of all, since we aren't bogging down the actual braking and signaling commands with heavy encryption, there's absolutely zero latency added to those life-saving, real-time actions.
By forcing safety and security to perfectly coexist through the black channel, engineers have beautifully solved this railway paradox. But honestly, as we step further into the future, it leaves us with a massive, provocative question for all of our automated infrastructure. As everything from our power grids to our cars becomes entirely digital, how will we continue to isolate the critical systems we trust our lives with from the open networks we can literally never fully trust? It is definitely something to chew on the next time you step onto a high-speed train. Thanks for joining me on this explainer today.